Enrico will join in a minute, and then we can start.
All right.
To this discussion session on integration of natural systems in wastewater treatment. And today we have Mr. Paul Skilicon, founder of Skilicon Technologies, Dr. Enrico Marsili, who is associate professor at Nazarbayev University in Kazakhstan. And we have Dr. Manik Dhanorkar, who is deputy director of Symbiosis Center for Waste Resource Management. And we have our experts here today. And first of all, the reason for choosing this topic for a discussion is the main reason is 80% of the water or the wastewater that is created is discharged directly into the water bodies without any treatment. And there are a couple of reasons behind why it happens. Is most of the treatment methods that people resort to these days is conventional techniques, and they have their drawbacks, and they have their restrictions. And in a country like India, the problem of wastewater is very decentralized, and there are smaller streams which enter into the nearby water body, in turn polluting the water body and destroying the ecosystem around. And these conventional systems are very costly. They are very difficult to maintain because their operation and maintenance cost is a lot. And I think that's why there is a reason for to come up with natural systems which are low cost, low maintenance. And I think people don't know much about these natural systems, and that is the reason today we have these experts who have worked in these different areas and have excelled in their projects. And it's better to have some guidance from them as the beginning of this discussion series or a discussion session. Now, with that brief background, I would like to ask Pooja to introduce Paul, and then he can begin his presentation.
So hello everyone, I'm Pooja Tendulkar, co-founder director at Lemnion Green Solutions, and I've been working with Paul for a couple of months in 2015. So it is a very, it is a pleasure to introduce you, Paul. So guys, Paul is currently, as Prasanna mentioned, is a founder, principal director, and at Skilicon Technologies Limited, USA. Since past 35 years, he has been working in various fields like water, wastewater, renewable energy, food, and municipal solid waste. And so currently and today, I want him to majorly speak about the sections where what are the opportunities and possibilities on natural systems in India and his international experience. So over to you, Paul.
All right. Well, thank you, Pooja. It's a wonderful to see you again, actually. So we worked together in Aula in India. Yeah. So let me see if I can make this work. Hold on just a second. All right. I think we're making progress here. Good. So duckweed, and I'm not going to dwell on duckweed at the moment. I've been told to move rather quickly. So I'm assuming you're all familiar with duckweed. Am I correct on that one, Prasanna? So let me just move on. Okay. It's not moving. Okay, there we go. So duckweed, this is Lemna gibba, one of my favorites, but I'll move on quickly. I started with duckweed a long time ago, in the mid 70s, actually. So some of you may not have been born back then. But I was working with UNICEF at the time, and we built thousands of latrines everywhere. And when I visited these latrines that we built, I noted that they were not being used. They would be used and then they got dirty and people just stopped. So they didn't have water in them. They were just a latrine, but nothing else. So I thought, well, if we paid people or they got some income from using a latrine, they would use latrines. So I looked to see if we could monetize what went into the latrine. And I looked at hundreds of plants, to be honest with you. And that's how I ran into duckweed. And this started what continues today, which is many, many years now. And I've worked on duckweed for that long. So we have learned to farm it. When I first looked at it, it was just a wild plant. No one was farming duckweed anywhere in the world. So we were the first people to really learn how to farm duckweed. That took a lot of work. We've eaten it directly. We've grown thousands of tons of duckweed over the years. And I fed it to just about everything you can imagine. There isn't a market for duckweed per se, although people are beginning to develop that market, but there wasn't. And so you had to monetize it by growing fish or producing milk or growing poultry, et cetera. So we fed it to just about everything. And we've grown it in every way you can possibly imagine over the years. We had a farm in Bangladesh, which is where we did most of this work, a 10-hectare farm, and we grew duckweed there. We co-cropped it with just about everything you can possibly imagine. This farm was recognized for 2 decades as the most profitable farm in the whole country of Bangladesh, right here. So we learned to farm it well. This is taro, which co-crops with it beautifully. Again, taro on one side, lentils on the other. We dried duckweed. We learned how to desiccate it rather easily in the end. This particular device looks a little crude, but this is only a 50-watt fan. And we collected heat very efficiently this way. We did about 100 kgs of duckweed every day. We even dried it fairly well during the monsoon. So we produced dried duckweed. And I'm going to stop for a second and talk a little bit about what drives me, development philosophy. Now, I am into rural development. That's what has always driven me. And I consider rural development globally to be an absolute failure. It is done badly. And what are the problems? Well, there's a very poor understanding of villages. Using an Indian context, the Indian administration doesn't know villages. They just don't go there. They don't understand it. This current issue at the center in Delhi with farmers is indicative of that. But it's shocking to me that there is this divide between the Indian administration, the government, and villages. And you have a top-down system which runs the country, and a bottom-up system in a sense that represents villages, and the two don't get together. We can go back to Gandhi, where the ideal farmer was this guy sitting with a spinning wheel, a self-sufficient farmer. That same concept, Gandhi's concept, has really been imposed on everybody globally now. In the States, you come here, a farmer is considered to be this self-sufficient person. His return on investment in the States is 2% return on his equity, which is nothing. It's a terrible return. Similarly in India, I'm working in Egypt right now. Same problems everywhere you go. The self-sufficient farmer, and yet the world out there is operating in a very different fashion. We impose on this farmer as well this microcredit, which I battle microcredit in a big way because it holds the farmer down. So I'm suggesting we need functional interdependence, and I have believed this for a long time, where you have high management, you have big capital, macro capital, and the villager. So those three, the nexus of those three, which is functional interdependence, and you have to have institutional functional interdependence, is where everything needs to go. All the cities operate in this fashion. I do what I do well, and I depend on all of you out there to do what you do well. And together we have this functionally interdependent thing called a city. We need to get that going in villages as well. And that's a massive problem that has been imposed on villagers everywhere. So we arrive at this first project, the Mirzapur project, which is about 1990 is when we got this going. And we designed it in the late 80s. And the idea was to use functional interdependence as a way to demonstrate that we could produce significant wealth at a village level. We, as a nonprofit institution, committed about $2.5 million. We got USAID to commit loan guarantees of 10.5 million, and OPIC, Overseas Private Investment Corporation, to provide re-guarantees to USAID on that 10.5 million. We then went to Sonali Bank, which is a government bank in Bangladesh, and we said, okay, we have all these loan guarantees. Will you lend this money? And they had a mandate where they had to provide 20% of their lending at the village level, but all their loans at the village level failed. So they said, okay, all guaranteed, et cetera. Good. So we also did one other thing, is we created a bank, so a bank branch, which we institutionally managed 100%. So we created this record, if you would, electronic record of a bank. We did all the work in that bank. So the bank didn't do anything. It had no transaction costs. And yet they loaned all this money, and all the money was paid back into the bank. So this was for them the most profitable bank ever in Sonali Bank, 100% rural. It looked great for them. So that's how we did this. So we formed a corporate structure then. This interdependence has to, we all have to be the same in a sense within an institution. So we formed corporations, not associations or whatever, a corporation. Local ownership was 67%, and our group owned 33% of this. We had boards of directors, regular meetings, et cetera, et cetera, et cetera. And this is how we function. Looking at the top there, we targeted 30 villages per district in 2 districts, 3 corporations per village. We had a simple rule that we couldn't go above 30% of the households, so that we weren't accused of politically manipulating anything. We were never more than 30% of households. So there's no politics involved. The household system then became a business plan. We went to each household and we made sure that they had water. Everybody got a tube well. We made sure that they all got toilets, that the toilets were water sealed toilets. They were friendly toilets to be in. They didn't smell. Everybody enjoyed going to the toilet. So water, toilet, we treated what came through that toilet, and we monetized it with fish. So that was the system. So if you look at how we structured this, this is an area in Bangladesh. You'll notice that each of these baris, which are an extended household, there's a lot of ponds around it. And the reason for this is they have to build up the house above flood level. So all of them had these ponds around, this space that was very poorly used. It became polluted. People drank from it and whatever. They defecated into it. And so this was the source of a lot of enteric disease. Everyone wanted to deal with this, and we had the way to deal with it. So what we did is we built a business plan around each one of these households. We built up the berms. Here you notice this is a fish pond next to a household. you'll see this squat plate, was a water seal toilet. So two of the elements of the system. There's a toilet going into the pond. We had a bamboo basket. And we also had these big bamboo mats, very heavy bamboo mats. And so if you had something that was bigger, a dead dog, for instance, or something that you wanted to rot, leaves, anything, we put underneath the mat into the water, and it slowly decayed there. What happened is this was so profitable, people ended up picking up all the chicken droppings, all the dog droppings, all the leaves, everything around the household ended up going into these duckweed ponds, where they essentially gave up their nutrients, and we grew duckweed. This is duckweed in one of those ponds. The duckweed was harvested on a continuous basis by family members in various ways and fed to fish in this fashion. So we took the duckweed, put it there, it was concentrated, the fish all came, ate it, and there was the system. We did carp. We learned we changed the way to grow carp. We set world records on everything we did. In the end, we were producing about 11 and a half tons on average per hectare of carp in each one of these household ponds, thousands of them. There is a typical system, fish pond. Harvesting fish, we would end up doing that ourselves. So we as the partner institution did all the inputs and outputs, fingerlings, etc. We monitored everything. We sold fish. We eventually did poultry as well, but we sold that into Dhaka, and it was a great partnership way it worked. Parallel to this, we also did a wastewater treatment plant with the Kumudini Trust, their hospital complex, and that's what this is. So we did two parallel systems. This is a wastewater treatment plant of a larger nature. This is, Pooja will recognize this. This is Aula, so she participated in this particular thing. We built it in 3 months. And the idea was to show a treatment of the waste coming from the factory's township and treat it to a level of 5 BOD out. So that was the test. And we beat that. So we managed to meet the standard imposed with something we built instantly, and we were able to treat it instantly. So this was, in my opinion, treating at a higher level than any municipal wastewater treatment plant when it came to reducing BOD, COD, and nutrients, anything in India. And we did it in 3 months. Boom. Treating wastewater. And this is just from the Aula system. Very quickly now, so we're moving forward. We've changed a lot of things, how we grow duckweed, what we do, et cetera, from the old days. And so this is just an example of a system that we are doing in, or we're working towards in Erode, which is a district in Tamil Nadu. The idea here is that we work backwards. So villages have been brought to a point where they all have toilets, but nobody treats what goes into the toilet. So a lot of that escapes into drains. There are some septic tanks, et cetera, but there tends to be a lot of runoff from these villages that have these toilets. We're working backwards. So we take what comes out of the toilet, we treat it and monetize it. We produce money with that in partnership with farmers, in partnership with the village itself, Gram Panchayat. And then the idea is to work backwards by then putting in sewerage, proper municipal solid waste treatment, et cetera, but working backwards so that it's paid for this way. There's no government money, nothing goes into this. So all of this is produced from the bottom up, and it's profitable. So that's basically the system that we're proposing. And this is just a view of the area. you'll notice that none of these villages have wastewater treatment, none of them. And all of them are producing vast amounts of waste. And all of that waste has immense value. So this is what we're proposing doing. You'll see here that they all have these nalas. If you go into the town, the nalas get bigger and they move out of the town and past, in this case, an SKM poultry estate. So we're recruiting SKM as a partner in this venture. They're a very modern entity, and they could deal with the duckweed. They can monetize it in part, although we prefer not to use what they do. But this is a nice way to do this. They can help produce the initial cash necessary to make a system like this work. Very quickly, the targeted estate, Nala, coming past the SKM facility, and there's 4.5. Now I've picked 4.5 hectares simply because that to me is a minimum size system that we can monetize. Anything smaller than that becomes difficult. So 4.5 hectares is my model. We use greenhouses. We have gone now to everything being greenhoused. We don't do duckweed in the open anymore. We have nutrient removal in these lighter green ones. And we have a polishing system in which we take the waste that has had all of its nitrogen removed, and you run it through a polishing system to take out everything else. So this is a wonderful, duckweed is incredibly inefficient at removing things from water other than nutrients. It just takes what it wants and that's it. But when you remove the nitrogen and it's looking for nitrogen, it processes huge amounts of water and it picks up everything, salts, trace organic compounds, heavy metals, etc. So we will take what comes out of the polishing system and that will be made into plastics. We will take what's produced in the non-polishing system, just nutrient removal, and we will make fish with that in this system. So we have a 3-dome complex, which is an incredibly efficient aquaponics system, much more efficient from an aquaculture point of view than other aquaculture systems, much more intense. And so this is our basic system. We have a digester array. We also bring in septage. We bring in municipal solid waste, so we get the carbon nitrogen ratios balanced. We generate a lot of cash. So that's basically it. Now this is about my first greenhouse system that I did 30 years ago.
Paul, sorry to interrupt you. You have 5 more minutes.
We're done.
Yeah.
Well, we're basically done. So this is a greenhouse, duckweed greenhouse, early system. We now do it inflated like this. So this is an inflated one. We use heat exchange membranes to keep the temperatures where they need to be, et cetera, et cetera. So this is a basic system. I've got projections here. Our goal is that a small family contributing a hectare can make 1 crore of rupees in a year. 2 workers and contributing 1 hectare. That's the goal. So that's our basic system. And I've left a description of it here, but you guys have access to that. If we want to discuss how the system works around questions, we can do that. We can do that here. So that's it. Thank you. This is Truro in England, so we're working on a project there.
Thank you so much, Paul. And I think we also need to think about such corporate-based systems that you're talking about. And I think the case study in Tamil Nadu gives a very good overview of what the system would look like and what can be done. in these areas. If someone has questions, I didn't announce it earlier, you can just drop it in the chat box and we can take them later. We'll have 10 minutes towards the end to address the questions.
So
so for the next, yes.
I'm going to do the stop share here. So we're back. Okay.
Thank you so much. So the next speaker we have is Dr. Enrico Marsili, and he obtained his doctorate from University of Rome in Italy in 2004. After doing a postdoc in University of Minnesota, he started working as a lecturer in Dublin City University. And in 2012, he joined Singapore Center for Environmental Life Science Engineering, that is CELSI, which is part of NTU in Singapore. And he worked as a principal scientist there. Where he developed methods of electrochemical characterization of biofilms and microbially influenced corrosion. His research interests, they span from bioelectrochemistry to biosensors and their use in bioremediation. And currently he is working as associate professor in Nazarbayev University. And he's going to talk about, since he has worked a lot in interdisciplinary projects, he's going to talk about interdisciplinary approach and how it can be implemented in wastewater treatment or bioremediation sector. Over to you, Enrico.
Okay. Good morning, afternoon, or night, everyone. Here it's 6 o'clock in the morning, so a bit of early rise, but it's fine. Let me share my presentation. Now, Prasanna was one of the graduates of the interdisciplinary research program, PhD program in Nanyang Technology University, Singapore. And the center where we were working at the time focused on biofilms. Biofilms, I'm bringing you back now one notch down with respect to what Paul has talked about. It's mostly about microorganisms, can be bacteria, yeast, fungi, and how they associate, they make a community, and they can use it for various functions. Now, since I suppose that not everyone of you is familiar with biofilm, I'll give a quick introduction by film and then just a couple of slides about interdisciplinary research and how can we contribute to that in wastewater treatment. Biofilm, it's this wonderful micro community, we call it the city sometimes, or the big fortress, in which bacteria, let me change the point, sorry, bacteria are encased in a self-produced matrix. This matrix, it's comprises polysaccharides, proteins, and extracellular DNA. It's very strong, mechanically speaking, and gives resistance to antibiotics, but also resistant to desiccation, an external digestion system that is able to destroy many complex nutrients or many complex pollutants for what it matters. It creates a very tight synergic consortia which are able to degrade and live on extremely complex nutrients. So this is a self-organized. We don't need to build it layer by layer. We need to learn how it works, so we control it. It's very heterogenic and dynamic, and these are the reason which is so difficult to use it for our purpose. Yet it's very promising, and you can say that most of the wastewater treatment plant in the world rely on some sort of biofilms, either as a patchy surface, patchy material on the surface, or more common as granules, where granules are these aggregate of biomass that are the basis of COD and VOD removal in activated sludge. Biofilms is basically all over the place. More than 99% of biomass in the world, on the terrestrial world, sorry, it's in the form of biofilm. Notable exception being the ocean snow and some biomass aggregate in the soil. Biofilm can be found in unsuspectable places like air conditioning, biomedical device, but what is important here, biofilm grows where water is. because of course it's microbial life, and grows where rich water is. When rich means rich in carbon, nutrients, or even in pollutants. So that's why biofilm is the most important ally when it comes to production of clean water. Biofilm has a life cycle. It includes cells that from planktonic state, from the normal free swimming state that you observe in a high school laboratory, goes into initial attachment. So find the surface, find an interface, and attach to that surface. Then the cell produces what we can call the matrix, indicated here as yellow material, maturate, grow in a very complex community, and eventually disperse for ecological reason to disseminate the species elsewhere and to basically invade part of the environment. Now, the timing depends on a lot of environmental cues, and timing this growth of biofilm is important for using it in productive plants like wastewater or bioproduction, biosynthesis. As such, biofilm has attracted a lot of interest in circular economy, because it's one of the most effective way to close the circle at the microscopic level before it goes to the plant and eventually to animal level. Biofilm is for plant and for unicellular organism or certain multicellular organism, what grass is for cows. It's a fantastic grazing material that helps to concentrate nutrient when you go from micro to macro. So biofilm is good in many ways, and Prasanna is one of the persons that use it as a positive force. Biofilm is good because it helps remove COD removal. Sorry, it helps remove COD. It helps remove a lot of complex contaminants. It's used in concentrating metals for bioleaching, and also helps with oil recovery. We work on oil recovery in Kazakhstan. And also is one of the main reasons for which we are alive. We are able to digest or extract nutrients from things other than sugar, because we have bacteria in our guts. Otherwise, we'll be completely naked without our microbiome, and we will die very soon. Unfortunately, although this is not a part of the scope of the day-to-day, biofilm is also bad. It causes a lot of infections, and it is probably one of the most important emerging problem in antimicrobial resistance and community infections. I will not talk about that today, but there's always a downside to things. So what I work on a very niche area called biofilm electrochemistry. Biofilms is a respiring community, like any other living community, and this respiring community can be we can monitor the respiration products, oxygen being reduced, nitrate being reduced, iron or sulfate being reduced, and through this monitoring we can detect and sense how much biofilm we have and which is the health of biofilm. Respiration is absolutely important, especially in anaerobic condition, because it's part of the nutrient removal process in wastewater, but also part of the detoxification in metal contaminated land. It's also part of oil souring in sulfate-reducing bacteria or corrosion. Prasanna spent a few years working on corrosion, although it's unrelated to the topic today. That's where he learned part of his skill set in microbiology. So my research, the part of my research that is relevant to this day, to this meeting, is the one on microbial sensor. Before introducing that, let's just give me one slide of classification. All microorganisms respire, and that is fine. Some microorganisms respire not intracellularly, so not inside the cell, but outside the cells. Basically, they are able to transfer electrons from an oxidized species, from a reduced species, which is nutrients like sugar, pollutants, acetate, almost everything, to a reduced species, which is oxygen, nitrate, sulfate, CO2 in certain cases, although it's a bit more difficult, and of course, iron, manganese, all the metals. I'm sorry. So we call the bacteria that are able to do this process strong electric agents, and they are used particularly in bioremediation However, most of the bacteria in the world can be termed as weak catalytic agents. So they are not respiring a solid surface as their prime mode of life, but under certain conditions, they can respire. And this can be relevant on large volume for biogeochemical cycling and even for producing a small amount of energy, which can then power our sensor. I don't think that we can produce independent energy from waste. I'm not one of the guys. Microbial fuel cells are fundamentally a failure at large scale. However, they can provide the sufficient energy for sensing, and sensing is the key process, the key part of this wastewater system, because without sensing, we don't know exactly where our wastewater treatment is going. So I think it's quite important that we develop a good sensor, and the sensor must be based on the same principle of circular economy that we apply in our plants. So we developed specifically a sensor with the help also of Prasanna and another person which is now today in the audience. The sensor uses biofilms attached to a little electrode, and when biofilm grow in normal water, can be actually contaminated water, so wastewater, is able to sense pollutants. Now, one of the biggest problems in wastewater is when you get a wave of pollutants due to illegal discharge, misregulation of the liquid flow in the plant, one of the millions of variabilities that lead to unpredictable water flow. Now, in many municipal wastewater treatment plants, this is sensed with few minutes before it reaches the plant, few minutes before it reaches activated sludge. Then there is a buffer tank, or even if you go to activated sludge, there is a redundancy activated sludge tank that take the place of the contaminated tank, because once the tank is contaminated, it basically stops working and create a problem in the water going out. The solution is absolutely practical, but it's quite standard in large treatment plant. When there's a lot of installation, lots of money, we're talking about, certainly not talking about rural area. However, when you have some discharge like that in a small plant with no redundancy and no defense, basically, you are in trouble. So early sensing of these pollutants in a sustainable way can help optimize the functioning of this wastewater treatment plant, not only for the process, but also for the public. So they minimize the release of smelly waste, minimize increase the water quality downstream, and so on. So this sensor, which is a toxicity sensor, works very well to detect organic pollutants, which are otherwise undetectable. Now, this was done specifically for industrial needs in Singapore, for the Public Utility Board, but we can certainly use this similar technology for detection of other pollutants, principally metal. Metal have a very strong toxicity, even in small concentration, but also oil product, certain detergent, and everything that is a strong alteration of the nutrient flow. And these systems are very small, can be miniaturized with minimal expenses. So I'm not sure how this will fit into actual rural wastewater treatment plant. Some adaptation is needed, but it's one of the technologies that can be considered. There is also this, the output of this technology is actually current, something can be measured with a simple battery and a simple device like a $5 data logger can give you a decent measure of the current. We actually implement that with a Lego built little flow device in the laboratory. We couldn't go into the field because, well, I left Singapore and the project got a bit difficult along the end, but I think that this is something that can be done. Now, besides the project itself, I would like to discuss here who does this project. This project requires competence, and many other projects in advanced wastewater treatment require competence in microbiology, engineering, in my case also electrochemistry, and within engineering we have at least a chemical, civil, and environmental. Now, we're not talking about one person, one heroic person doing everything alone. We're talking about a team that must comprise interdisciplinary researchers that are in the beginning, even at the bachelor level, so the first degree level, trained in at least 2 fields. So they can bridge with other professionals working in a team and can be much more effective for implementing work, creating industry, and so on. Now, this program requires, of course, on quite exceptional individuals. I'm not saying that this is an easy task, and the selection was brutal, and I don't see how this can be scaled up to a larger number of people, because you require special talent. However, once you have a few people with this special talent of being multidisciplinary, you can use it as a catalyst to create an industry, to create a training program for sure, to diffuse this kind of research or operation in the general population. So I do believe that we need, at certain point at least, exceptional individual to spread the interesting invention and to diffuse it. Then, of course, the community can take over, but we need some initiator. I don't think that we can do everything from at the same level. We are not equal. However, this program was very successful, although painful, and the two of the graduated persons who co-supervise are Prasanna and Lucinda. Lucinda is now actually assistant professor in IIT Delhi, so we can definitely call a success story. And although my sample size is not very big, here n is equal to, I can certainly tell you that it is by far a very successful program and a very successful approach to implement. Maybe not at the same level of resources that we have in Singapore, because we enjoy a lot of money in Singapore, but some hint, some aspect of interdisciplinary training must be included in any course, any degree in the world. I'm actually teaching right now, I finished yesterday, an intensive course in biofilm to a pool of interdisciplinary research students between undergrad, grad, and PhD. It was a model after the Celsius Summer School, Prasanna. So 2 weeks intensive. Unfortunately, I'm alone, but next year we'll turn to something bigger, in which we teach various topics, biofilm, medical application, environmental applications, and try to show the students the complexity of this world. Some of them probably just take it as a cycle of lecture, learn something, okay. But even if 1 or 2 of them out of 100 decide to go into research or open a startup in the new team, most important team of circular economy, that would be great. I'm working with an institution called the University of Bari in Italy, and I have a strong interest in circular economy. And in fact, I would like to later to diffuse this lecture and send to my colleague there. And we plan to have a long-term collaboration in this area. So I think that my talk is short today, because I'm not here to present any particular advancement. I'm just an average researcher, but I will be very happy to respond to questions and to show how this kind of research can be implemented in a rich country, Singapore, so-and-so country, rich but complicated country like Italy, and definitely developing country like Kazakhstan. I think the approach is can be modulated in various ways. And with that, I don't even have the visual campus. Right now it's covered in snow. Kazakhstan is very cold, so we cannot grow duckweed there. We can barely grow anything, but we can grow competence and talent, that's for sure. Thank you.
Thank you so much, Enrico. Thank you so much for a wonderful session. And I guess all the
I think we lost it.
Yeah, I think Pooja has some connectivity problems.
Hello.
I think now she's back. Yes.
So thank you so much, Enrico, for the wonderful session on biofilms. And so I request everyone to stay back. I request Enrico also to stay back. We'll be taking all your questions regarding biofilms at the end of the session in last 10 minutes. And now I invite the last speaker of this session, Dr. Manik Prabhu Dhanorkar. So Manik Prabhu Dhanorkar is associated with Symbiosis University Pune, and Dr. Dhanorkar is heading the Symbiosis Center for Resource Waste Management since February 2017. And he has a doctorate in botany, and he has worked with Government of India on developing world-class encyclopedias on fertilizers and pesticides for 14 years. He also has an industrial experience of 7 years, where he has developed a business model for commercialization of biomethanation by integrating it with indigenous technologies. Today, Dr. Dhanorkar will be sharing his experience on research-oriented wastewater problems and innovative ideas. He will also be speaking about importance of industry and academia collaborations and his experience with working with Lemnion. So over to you, Dr. Dhanorkar.
Thank you, Pooja. And am I audible enough? Yes. Okay. So I'll share my screen now. Okay. Can you see my screen? Okay. Basically, on the occasion of this World Water Day happening tomorrow, we will be discussing here the sustainable waste management, wastewater management technologies, and the research happening in India. As we all know that water is a very important resource on the planet, which is important, which supports our existence, and it is important for every kind of life on this earth. Though this planet has about 70% of water, though the earth is covered with 70% of water, most of the water is salt water, about 98% in the seas, and about only 2% water, which is readily available and supports all life, major life, or the terrestrial life, we can say, fresh aquatic life. That is only 2%. So this 2% water, if we see the further distribution of it, about 68% of the fresh water is locked in ice caps and aquifers, and about 30% in groundwater. What is readily available is about 2% in rivers and lakes. And this is what is being utilized by humans for their needs and purposes. Now, my question is whether these 2% of water, or whatever the fresh water percentage on the earth, is it inadequate to support the life? If it were to be inadequate, this planet would not be surviving for the last so many thousands of years. So the water, this water as a resource is there on the planet like any other resource on the planet, and it is being recycled within the planet in various forms, like salt water, fresh water, and ice and everything. So nothing comes from outside. What comes from outside this planet is only the solar energy. That is important for our life. So this water content available on the planet is quite sufficient. But then why we are being why the world is being forced for this water crisis, water scarcity? It is because of the irrational use of water by humankind. On the right hand side of my screen, if you see, there is a comparison of average per capita water usage in the developed countries in US and in the developing countries. Here is an example of in India, about 38 gallons per day as against 156 gallons in US. So there is a vast difference. Even this 38 gallons per day in India is a huge quantity of water. And to meet this demand, apart from when this river and lake water is not available, people are going towards the groundwater, and which is also depleted now. So this is what is driving for the water crisis. So if we take a look at the world water crisis status, we will see that half the world is already facing very high stress, high to very high stress of water. Most of America, I mean in the US, most of the Asia, northern and southern parts of Africa, Australia, they are already facing very high water stress. If we look at the Indian scenario, it is quite evident that more than 54% of India is already facing acute water stress. And whatever available water is there, more than 70% of water is contaminated and is not of drinking quality. If you look at the graph, the per capita average annual availability of water in India has already decreasing. We have already crossed the water stress line and approaching maybe in another 25, 30 years, we will be touching the water scarcity line. Let us have a look at this scenario. These pictures are quite familiar to us. We normally see these pictures in summers, in newspapers and TV channels, news from urban areas, news from rural areas, how people are struggling to get few liters of drinking water. Now, why is this situation? Yes, it is attributed to the growing population. But most importantly, it is the use of drinking quality water that is being irrational use of drinking quality water for non-drinking purposes like agriculture, industries, construction, and so on and so forth. And because of this, there has been limitless withdrawal of groundwater reserves. That is why we are facing the water stress or water crisis. And if this continues, if the situation doesn't is not taken seriously, then with the demand of increasing water, the future appears to be extremely uncertain. Therefore, it's need of the day that we must learn to value water, and that is why the theme of this year's World Water Day is value water. So what can be done to improve this current situation of water scarcity? Yes, there have been many initiatives taken in India worldwide to conserve water through various water harvesting technologies and initiatives, rainwater harvesting and so on and so forth. However, are you able to see my screen? Hello?
Yes.
I'm not able to show. Just where is it going?
Now we can. I think there was some problem.
No, you can. You're not seeing me. You're not able to see this.
We are not able to see the presentation though. But
Yeah. I don't know how this got off. Let me check.
Yeah, sure.
This is the problem with virtual meetings mostly. Yeah. Is it visible now?
Yes, it is visible.
Yes. So the initiatives for water conservation are being there. There is some improvement in the groundwater levels, but what is the most promising area is the wastewater that is being generated through the irrational use by humankind. Okay, so increasing wastewater and the wastewater being generated, the disposal of that wastewater is already the current global environment concern. So how we can reuse the water? If water can be a part of solution to water scarcity, how to use this water, wastewater, to treat and reuse? First and foremost thing is water treatment or the wastewater treatment using safe and efficient technologies. This treated water can also be used to recharge aquifers to reduce water stress. And it can be a reliable water supply for agricultural irrigations, where now, even today, a huge quantity of drinking quality water is being used. Let us have a look at wastewater generation in India just to understand the scope of wastewater treatment and recycle in India. This wastewater generation, I'm talking about only the sewage treated water, sewage water and not the industrial water or any other agricultural wastewater that is being generated. Just to get an idea on the scope of quantity of water generation and the scope for treatment, here we see that about 72,000 million liters of sewage is generated in urban areas in urban India. There is provision of about 1,641 STPs, out of which only about 1,100 are functional. And these have been able to treat only 30% of the sewage generated. Forget about the other industrial effluent treatments, effluents, or any other irrigation, agricultural wastewaters, and so on and so forth. So there is a huge scope to treat about 70% of untreated sewage, which is directly being disposed into the environment. Why is this happening? Why only India is able to treat only 30% of water? As Dr. Prasanna has already mentioned, these conventional water treatment technologies, which are like sewage treatment plants, effluent treatment plants, or like combined effluent treatment plants, their first and foremost, their capacity is insufficient to cater the quantity of wastewater or sewage that is generated in India. Secondly, they are very cost intensive. They're energy intensive. They need skilled labor for skilled labors for operations, besides other operational difficulties. And being energy intensive, these conventional treatment technologies have been contributing to greenhouse gas emissions ranging from 3 to 7% of all the emissions. So our literature study has identified some promising research areas where we can concentrate to improve the situation and improvise the efficiency of wastewater treatment, either giving separate standalone technologies or in combination with the wastewater treatment technologies. So these promising areas could be natural wastewater treatment systems, membrane filtration technologies, biofilms like Dr. Enrique just mentioned, then advanced oxidation processes, biological filtrations, anaerobic processes. Also, one of the promising areas could be reducing the energy conservation required during the treatment. So need of the hour is to improve, to provide novel technologies or the existing natural based systems, wastewater treatment technologies, which are very low cost, which are very low, with very low energy requirement, with very low investment, and very low carbon footprint as well. So what are these natural wastewater, natural systems-based wastewater technologies? One is water hyacinth ponds, duckweed-based wastewater plants, what Mr. Paul has just presented. Waste stabilization ponds, which are commonly used in Indian context. There are reed-bed wastewater treatment technologies, oxidation ponds and lagoons, fish ponds, and natural and constructed wetlands. The benefits of these natural wastewater treatment systems, there are multiple advantages and applications. First and foremost is they are ecologically safer and sustainable. They are low maintenance and highly economical with less energy requirement, and therefore they contribute to reduction in greenhouse gases. They do not require any skilled labors. These can be built to any required size and can be decentralized to the smallest quantity of wastewater that is being generated, mainly in the rural areas. I will highlight this point because in Indian context, mostly in the urban areas, centralized wastewater treatment plant is being mostly adopted and are functional. But this being very cost intensive, the replication of these systems into rural areas where the wastewater generation is low and needs to be addressed in a decentralized way is being very difficult. So that's why we need these natural wastewater treatment systems. These systems are also scalable. As I have mentioned, from small size to what Mr. Paul has presented to a commercial level size. Secondly, and most important thing is, it's not only the wastewater treatment. As Mr. Paul has already mentioned, these systems could be sustainable technologies in terms of various uses, like biomass use and value generation, or the development of value products from this biomass, and many other applications. So the Indian scenario on research and use of these natural treatment systems shows that current scenario with the conventional systems is insufficient in wastewater treatment and management. Therefore, there is a need of novel methods that should meet the drawbacks of conventional systems and improve the treatment efficiency. The choice of treatment, national treatment systems have been the choice for the treatment of wastewater, and are proven to be better alternatives to wastewater treatment worldwide, because it requires minimum energy, and they are sustainable because they reduce maintenance cost. However, adaptation of any new technology for its practical applicability in Indian scenario needs assessment for economic viability and endorsement by public bodies and communities. This is very important in Indian context, because most of the technologies, government or the local governing bodies, they prefer imported and high cost technologies. And if we go to rural situation, rural India, the provision, the financial provision for developing or installing such, implementing such technologies is very, very low. And therefore, cost effective and low maintenance technologies is a need of the day. Therefore, it calls for an in-depth scientific investigations in the natural treatment systems through research to understand efficiency of these systems, to develop functional models that can serve communities to assess whether natural treatment systems could perform as a standalone technology or need to combine with conventional systems to improve the current situation of wastewater treatment. Government of India has already therefore given top priority to the joint public body community participation, which plays a significant role in wastewater management, in addition to control and mitigation of the environmental pollution. Now, as we see, about 65 to 70% of India is rural population, and it demands low cost, user friendly and low maintenance value generating systems for acceptability. One important thing that requires to be highlighted here is that development of local indigenous technologies is very important, because they can only be sustainable technologies, simple and user friendly. But government, local bodies and community should adopt them. There should be accessibility for such technologies in India, and there should be adaptability of such technologies for decentralized applications. So therefore, integration of traditional treatment systems with natural systems has to be, and this has already been tried in India in certain places in UP, Punjab, Madhya Pradesh and Andhra Pradesh. And there are few plants demonstrating such integrations with the conventional ones, which I have highlighted here. I've showed here with the red arrows that sewage treatment, conventional sewage treatment is coupled with anaerobic or facultative ponds, water acid ponds, fish ponds, like aerated ponds or the constructed wetlands. And they have been functioning efficiently than before. So such systems can work, but there is also important to conduct research whether these systems can work as a standalone technology, as a standalone system, and still be cost effective and efficient. Among the natural treatment system, the most common systems are the waste stabilization ponds, which account for about 73% of the existing natural treatment systems in India. we can see that the natural wetlands and constructed wetlands can also act as waste stabilization ponds, which are the simplest of all waste treatment techniques. And hence, assessment of these natural treatment systems for techno-scientific, economical, and socio-public levels is mandatory before its implementation at a large scale. So realizing the importance of research and techno-scientific need, Symbiosis Center for Waste Resource Management, in collaboration with Lemnion Green Solutions as industry partner, has initiated research on duckweed-based wastewater treatment systems. The broad objectives of our collaboration is to undertake research and develop scientific data on duckweed-based wastewater treatment systems, to develop cost-effective, scalable, and replicable technologies and the functional models to demonstrate, explore potential of duckweed biomass for other applications and development of value products so that it becomes sustainable and can fetch some revenue to make it sustainable and self-sustainable. And as with the industry partner, implementation of sustainable projects for communities, industries, agriculture, so on and so forth on larger scale. Here I'll show you some graphs where we conducted research with duckweed-based treatment systems in laboratory conditions and in natural conditions with different inoculum size. And we have been happy to receive good, encouraging results in terms of critical parameters that are monitored in wastewater treatment, like BOD, COD, total dissolved solids, oxygen, dissolved oxygen, so on and so forth. So in both the conditions, in laboratory situation, laboratory conditions, the results were studied with different inoculum sizes, and the better results with little scaled up size, we have observed similar results in natural conditions as well. So this is boosting. There are a lot many results that can be presented in detail, but due to time constraint, we will not talk much about this. But these systems have been proven to be very effective. We are also exploring through this collaboration the roles of associated microorganisms with duckweed in wastewater treatment. We are already working on wastewater treatment using this aquatic biomass. We have also concentrated on animal, poultry, and fish feed and fertilizer and soil amendment areas where the biomass can be effectively utilized. Adsorption of metals is another area, or some human superfood or supplementary food. This can be explored, but due to the some research constraints, to the constraints of manpower during this COVID situation and all, these areas, as of today, we have not touched, but we already are working on the role of associated microorganisms, feed preparation, fertilizers, soil amendment, and wastewater treatment. Here are the glimpses of the demonstration plants of life-scale plants of duckweed-based wastewater treatment projects implemented by Lemnion Green Solutions in Pune. And they have been fantastically working, and the local governing body is very happy with these interventions. Now, what is the need of the day? Having the industrial experience and now being in academics, we have realized the need for a teamwork. Yes, for any technology development or technology improvement, academia and research has to be there to study the scientific nature of it and to study the feasibility of any technology. Scientists can do this work, but scaling of these technologies and community outreach or commercialization of this needs to be handled by the industry. Because researchers cannot directly go to the field of view. Even if they are good, they don't have the knack of doing it commercialization or scale or community outreach and so on and so forth. So industry contribution is very important. And of course, there is a role of government. As I have already mentioned, acceptability or acceptance of local indigenous technologies by local governing bodies and government rather than emphasizing on cost-intensive, centralized, and important technologies is very important. So for translation, policies, finance, and implementation, the role of government becomes very necessary. And then only if these three areas combine, India, academia, industry, academia, and government, they collaborate, the sustainable technologies can be really developed and installed to cater the need of wastewater treatment so that water stress can be effectively reduced. I think I'll stop here, acknowledging the team this is team SCWRM. We would like to acknowledge Lemnion Green Solutions for initiating this event and inviting us to talk into this event. And of course, to Symbiosis International University for encouragement and guidance and their support for whatever the activities we are taking at this research center. Thank you very much.
Thank you so much, Dr. Dhanorkar, for the detailed presentation and giving us an overview of what's happening in India and what should be done, or how the best slide was, I think, how industry, government, and academia can come together and have a common approach together. So we have a couple of questions, and let's start with, I think, Paul, this question is for you. It's what is the groundwork or field work that you need to do in these villages before you identify what kind of interventions you're going to do in these villages?
Okay. Essentially, we need to find the waste. So in this particular instance, I looked at this with Google Earth, and you can see the nalas easily. We sent people in to the village to identify these nalas, see where they came from, what was happening, to talk to the sarpanch or the gram panchayat people. And they're very happy to have this treated. In fact, I've not come up with a gram panchayat that didn't want their nalas treated. So that's easy enough. And then you have to follow up and find out what's happening in that particular village to septage. Where is this stuff from all these toilets going right now? Septic tanks. If they have septic tanks, who's picking that up? What's going on with it? We have a requirement to balance nitrogen and carbon in our systems. We do advanced anaerobic digestion using biofilm in our anaerobic digesters, by the way. And we do sequenced anaerobic digesters. There's nothing in one big pot. Everything is a specific sequence using biofilm in the digesters. So we need carbon, we need nitrogen, we need to balance carbon and nitrogen. So we need to go looking for enough carbon. It's typically, you can find it, municipal solid waste, a plant that is producing fats or oils or sugar. We need to do that. So collecting, balancing your carbon, nitrogen is a key. And then you've got to do a plan. So, you've got to build digester array that costs money, and we need to make sure we've got the inputs for it. We need to look at markets. We need to look at, for instance, in this system that I showed, we will produce primarily fish and plastics. So if we're producing plastics, what are we going to do with those plastics? Where are they going to go? Do we need to value add one more step? So instead of just producing plastics, we add fiber and we produce an advanced, using two types of plastics we produce with the duckweed. And that copolymer we blend with bast fiber. So jute is a good bast fiber. Is there jute around? We use kanaf because we use the kanaf core as our biofilm. And so we would prefer to just grow some kanaf. We use the biofilm internally, and we use the bast fiber internally to produce an advanced bioplastics. So all of these things have to be designed. You've got to do a business plan. You got to have markets, et cetera. You've got to raise the money to do it. But the amount of revenue that these generate is staggering. So the return on investment of a rural wastewater treatment plant is better than building a hotel, better than having whatever. It is extremely profitable. So, you know, my vision here is that ultimately rural India, which is forgotten, will be the place where we can do all these things in small systems. 4.5 hectares, to me, 5 hectares is the minimum limit. So learning how to aggregate 4 or 5 hectares requires very sophisticated thinking in India, you know, because everybody's got 1 biga, 2 bigas, 3 bigas, or whatever of land, and putting it together as a 4.5, 5 hectare system is not trivial. So, and then they have to be brought in as partners. You know, what are the terms on that partnership? What do they get up front? You know, long-term leases, et cetera, et cetera. So it gets very complicated. But my view is that the potential to make money this way is huge. So for instance, take these people that we did in 1991 or 92, all these villages in Bangladesh, just treating their wastewater gave them toilets, got rid of all the waste around the home completely. It gave them water. So everybody had water, everybody had toilets, etc. Got rid of disease. And we made for each one of these families 10 times as much money just on their toilets as they made in their crops. So they have fields that they grew mustard, they grew rice, they grew whatever, which are commodity crops they get nothing for. I mean, a farmer, it's like putting a gun to his head every time he grows a crop. It's just commodity crops. He gets nothing for his rice, he gets nothing for his wheat, he gets nothing for his mustard. They grow turmeric in this place in South India, so they get a bit more for that. But a farmer makes nothing on his crops. If we join with him and we put in big capital, right? We put in advanced management, advanced technology, and we join together as partners, complete. Now, partnership is forever. You don't walk away from it. That farmer with 1 hectare committed can make not 1 lakh, he can make 1 crore, just treating wastewater. So that is where we are hoping to go. And then what do we do with the water? You know, I have visited many, many wastewater treatment plants around the world, thousands of them. And not one plant, if you just take a random sample, go to that plant, look at the outlet, not one plant is treating to whatever standard they're supposed to treat. Not one. I mean, I can go to New York City, they're not treating to standard. I can go to Delhi, anywhere, not treating to standard. So we have made a commitment that we will treat to only one standard, potable. So our systems treat, they remove everything. The duckweed has to go through a 2-phase process. We can remove salts, heavy metals, trace organics with duckweed with unbelievable efficiency, much better than you can with activated sludge. And I do activated sludge. So I've got the most advanced activated sludge system going right now, which is with a company called Nuvoda, which I think Veolia is going to buy that. But it's, yeah, activated sludge can only treat to a certain level, even with advanced biofilms. We, with duckweed, can desalinate. We can desalinate water. We remove salt ions. I mean, it's stunning what we can do with duckweed. Then we take that water, which we have sucked everything out of, in 2 phases, and we run that through a membrane. Now, we lower the surface tension of water. So this is very advanced stuff. Now, lowering the surface tension of water is not trivial. It is, people don't know how to do it, but you can lower the surface tension of that water and you run it through a membrane at 1/3 of the power that you would require otherwise. So we produce then a water that is better than any piped system that you will get in any city in the United States. And we'll do that with wastewater in a village in Tamil Nadu. The water I drink in my tap here has estrogen, it has ibuprofen, it has medicinals, it has all kinds of stuff in it. The water treatment plant can't remove it. In India, it's just shocking what you get out of the tap. It's just absolutely stunningly bad. And any place where you turn the water on and you turn it off, it sucks sewage in every time you turn it on again. And so every system that is rationing water, which every Indian city does now, is sucking in wastewater. So, yeah, this is disgusting. We treat only to an advanced potable standard what you would get out of a bottle on the shelf. So that's all we will treat to, period. We don't take any other standard. And we're going to do this wherever we treat wastewater. So it's a very complicated system. See, I mean, you talked of simple, no, it's very complicated, but it makes money. Right. And the key thing here is we extract all the energy and we monetize it. We extract all the nutrients and we monetize it. And those two make the money.
No, Paul, there is a follow-up question which is a bit more scientific. And since duckweed has a very high growth rate, can we actually use duckweed for carbon sequestration? And can we show that as one of the profits?
Yes. So, yes, you can. But to do carbon sequestration, you've got to produce a material. So what we do is we take duckweed and we produce from that duckweed 2 types of plastic. We produce a PLA, polylactic acid, which is easily done. And then we produce a protein plastic. So those 2 plastics, protein plastic and PLA, we blend to produce a copolymer. So it's a very good plastic. And then we add to that bast fibers. And if we produce, if you produce a lumber, so we grow arundodonax, but you can do bamboos and so on and so forth. But arundodonax fiber is the fastest growing lignocellulosic material on the face of the earth. You take that, you take canaf, which produces the finest biofilm on the face of the earth, which we use internally, but the bast fiber of that, like jute, you add that, the arundodonax and the bast fiber, and you make lumber, engineered lumber, using duckweed plastics as the binder. Now that engineered lumber, you can sequester. You make buildings or whatever of it. The other thing we do with the plastic is by using a natural fiber as a reinforcer in that plastic. We can use it in vessels that we can put food and so on into. But the key thing is a bioplastic copolymer with natural fiber reinforcing. What happens is that natural fiber inside it, as opposed to say fiberglass, it kills the UV degradation. So while ironically you're producing a bioplastic, but by reinforcing it with natural fiber, you kill UV. I can put natural fiber into polypropylene and polyethylene, and I can take a bucket of that and put it in the sunshine, and then 10 years later, it will still be fine. I can take a bucket of polypropylene and polyethylene and put it out just by itself, no natural fiber, and it'll fall apart in 3 years. It degrades. But natural fibers render that plastic immune to UV degradation. So that thing that you make, plastic, engineered lumber, etc., all of that sequesters carbon, and it will do so for 100 years.
Okay. There is a question for Enrico. Enrico, in India specifically, monitoring of wastewater is a big problem, and monitoring the parameters as well as monitoring the flow. So, and most of the times electrochemistry sounds like a costly affair. So, are there affordable and durable sensors which can be used for, I would say, wastewater policing?
Okay, that's actually a question that great question that they ask in Singapore, and Singapore is not has a lot of resources. Yet we couldn't find on the market any cheap, clean, and durable approach, because this would be a Santa Claus of approach. So we are working hard on at least on one side, which is durable. Then, to be honest, if you have to use a couple of batteries to power a device in a small box, and as a reward you have clean water, well, we do with cost benefit analysis. You say, okay, a couple of batteries can be used. So I think there is a way to develop a sensor, but you cannot at the same time have a clean, cheap, and durable sensor. We need to work around that way. Ideally, we want sort of what we call a P1 sensor, so early alarm, a sensor which is fairly cheap and fairly unimpactful, that tell you something is wrong here. Then you send a person. You cannot have a complete screening of what's going on. That would be too expensive. I think that that this kind of option of based on paper sensor, origami sensor, or a disposable sensor, it's very, very, very attractive, especially when you can access the environment like it was for the treatment plant. So yes, I think that there is, but we are still working on it.
Okay, thank you. And so now we have three experts from three different backgrounds, and I think that's my question. I think it will be an interdisciplinary question, and I would like to target it to Dr. Dhanorkar. We have talked a lot about duckweed, and we have talked about electrochemistry, and we have talked about biofilms, and with SCWRM, we are also working on characterization of these biofilms, and I would like to know about how these three things can be integrated together: use of electrochemistry for actual monitoring and characterization, and duckweed knowledge to maybe by understanding the microflora, we can increase the efficiency and things like that. So I would like to know more about the integrated approach in SCWRM.
Well, yes. As you have asked for some, cost-effective monitoring systems for wastewater treatment, already Government of India through Central Pollution Control Board have compelled monitoring of wastewater treatment systems, even at a society levels, where the small wastewater treatment STPs are installed or ATPs are installed. But again, installation of these monitoring systems are even a costly affair, and there have been many companies popping up with the intention of making money. Okay, so like Mr. Enrico has mentioned, so there is a need to develop some cost-effective technology monitoring systems as well. Now at SCWRM, yes, we are working on, of course, we are not into sensors, but not in SCWRM, but we have some research centers which are working on developing sensors at Center of Nanoscience and Nanotechnology. We have experts here. So we are working in collaborations where wastewater treatment can be monitored, or the systems can be monitored for effective delivery of wastewater or the treated water. Regarding biofilms or the microorganisms associated with duckweed, my colleague Dr. Pooja is working on this thing. She is a microbiologist, and the Department of Science and Technology woman scientist with SIU. She has recently joined this SCWRM. So maybe Dr. Pooja will highlight on this. Dr. Pooja, are you there? Can you unmute?
Yes, I'm here.
Yeah.
Yes, yes.
So can you please highlight on the microorganisms that we are isolating and working on it?
Oh, hello, everyone. So as Prasanna mentioned, and then Dr. Dhanurkar said, we need to integrate a lot of interdisciplinary approaches for treating or tackling a particular problem. So what at SCWRM we are targeting is, as Paul mentioned, first of all, commercializing that particular technology. So whatever we are getting, that needs to have some commercial importance for the people involved in it. And that is how we can make a sustainable technology. So one aspect of our research at SCWRM is to make that technology sustainable. How much of value can we get out of it? So we are working and initiating research on different aspects of the use of biomass. One is starting to check whether how feasible it is as a poultry and a fish feed, which is already done, but that is one channel which we are doing. The other is to check the palatability of the duckweed as a superfood. So we know that duckweeds have been used since centuries in salads and all in Vietnam and all. We want to develop something like we have spirulina capsules. So we want to develop something on those lines for duckweeds as well. As far as the monitoring systems are concerned, so as Dhanurkar mentioned, we have the SCNN department here. They are into developing bio-based sensors for tackling particular component in wastewater, say for example, heavy metals, or say for example, some hormones. So with integration with them, we are also trying to figure out if we can have some monitoring systems which we can install in the wastewater along with our duckweed-based systems to in situ monitor the various chemicals and the molecules present in the wastewater. So that is one aspect which we are going forward is in terms of research. The other is, as far as microorganisms are concerned, there are some organisms which produce molecules like biosurfactants. I think Paul mentioned that we need to reduce the surface tension of the water to make it more, economical for the membrane to handle. So that is one of the aspects which can be explored in the sense that we can use these organisms which are already associated with the duckweeds once we are done with the research and all. And one of those organisms would be the ones which would be producing efficient biosurfactants, and we can use that organism to kind of be a key player in the reduction of surface tension in the water. So these are the various, there are a lot of research which can be done, so there are a lot of ideas which are there. So we need to focus on these ideas, problem-based ideas, and then tackle one by one these systems. So yes, we can use these microorganisms to integrate in our duckweed-based systems. We can use biomembranes as part of the integration systems. And we can use even other natural materials as part of the adsorption, which would reinforce the duckweed-based efficiency, the system of the efficiency of the system. So that's from my side.
I would like to add here, Mr. Prasanna, Dr. Prasanna, it's not only wastewater treatment systems, all the even solid wastewater treatment systems, whatever is implemented in India, they are not being properly monitored. So the monitoring systems is a need of the hour, so that whatever we are delivering as a treated waste or treated material or water, that's why, because of the absence of these monitoring systems, there has been a lot of problems. So definitely we need it.
If I can add just one comment on that, there is a huge disincentive to everyone that manages a wastewater treatment plant not to monitor, okay? Because they all cheat, okay? They cheat in New York City, they cheat in London, and they cheat in Delhi. So, this is chronic. The whole system cheats because it's expensive to treat. And so, it's a very tough thing. A small kit this big, I can go and in 5 minutes I have samples and I can take, it's very easy and simple to monitor wastewater. It's not a problem. It's just nobody wants to. And so you can try all you want, but the disincentive on the part of officialdom is huge. Every single talab, every single river, everything in India is polluted to a point it's just staggering. And yeah, we got to change that. And the only way you will change it is by monetizing it. Extract all the energy, extract all the nutrients, monetize those, make money from it, and the problem goes away. And only produce potable water. So as soon as, standards, what do I treat to? 5 BOD or 10 BOD, whatever. No, only potable, only potable. And there's no ambiguity on potable. No ibuprofen, no estrogen, no anything in it, and only so many salt ions. That's it. So that's where we've got to go. And I think all of us have to get together to ensure that that's where we go. And then the water is worthwhile, There's not a single city in India, and I've looked at everything in Pune, I'll tell you quite frankly, that is treating wastewater to a reasonable level. Not one single treatment plant, not one. What is that, They're putting in these new systems, Ganga, and you go to any one of them, not one of them is treating to even a reasonable standard. Potable, it's got to be potable.
Yes.
So that's my message, that's my mantra, it's got to be potable.
Of course, there is a lot of work which needs to be done. And I think apart from the systems, oh yes, Dr. Dhanurkar, you wanted to add something?
Yeah. Thank you. If you allow me, Dr. Prasanna. Dr. Paul, I was very much curious with your presentation, and Government of India is anyway encouraging public-private partnership. Okay. I know that government is not shelling out a lot of money, basically when it comes to water or solid waste or wastewater treatment. But to make it more, economically viable project, everything needs to be monetized, as you said. And you have fixed the size of your system or the ductile system to be commercially viable, that is 4.5 hectares, right? So can you please tell me what would be the population size of the village if I want to go to rural India, or the quantity of wastewater treatment that needs to be generated for that 4.5 hectares? Because there are many small villages where maybe that amount of wastewater generation is not there, or even if it is there, there are not many, every household will not have toilets because there is a lot of open defecation. Okay, there are no systems to collect this whatever wastewater is being generated, because households may have some pits, or they must be releasing water openly in the fields and so on and so forth. So developing an infrastructure to collect this wastewater is also one thing when it goes to decentralization or for small scale villages. So can you please comment on this?
Remember, I talked about this first system that I put together in Bangladesh in 1988, 89. We treated the wastewater from every single household.
Okay.
And the wastewater paid for a tube well, a toilet, and it made more money for them, just that wastewater, than their crops. So, this is doable. You can do that same system we did is doable today. This was back in 1988, 1989. It's doable today. We have much better technology available to us today than we did back then. Yes, it costs more at the margin, but we can grow more fish. We can grow more chickens. We know how to do things a lot better than we did back then. And back then we made stunning amounts of money. So every household in a village can be done. Villages tend to aggregate so the houses are together. And so you have to sewer those typically, and sewering a village is problematic. It takes time and effort to do that. So initially you have to take what you've got. Yeah. Kya mil sakta hai? So you've got to take what you've got and treat it.
Yes.
And then go back in and develop your sewerage system to collect more. but it's not a problem. You take me to any village in India, I don't care, any village, whether it's in Rajasthan or Tamil Nadu, and you can put a system together that will make money.
My intention was to only to demonstrate, because I want to have some model somewhere, because the Symbiosis International University has adopted several villages as their social responsibility or for community outreach. So we don't want to give anything to them as free of cost. Let there be a participation from the villagers or the communities as well, and we give them the technologies and you know, technical guidance and technical know-how. So that's why I just wanted to know how this financial model works or how it can be implemented at distance.
I go back.
Very happy to interact.
I go back to my theory of functional interdependence. Okay. Today, every urban location in India, every city functions that way. It is functional interdependence. In other words, I am an accountant, he's a lawyer, he's a taxi driver. We all do what we do, and we do it very well, and we all depend on each other in this system we've got. The problem is that in a village, that's not the case. So, you know, you say, I'm going to go help this village. Well, how can I help this village? Well, you give them some technology. It doesn't work. Okay, it just does not work. So what has to happen is you have to be able to join with them.
Yes.
Okay, forever, not for 10 minutes or 10 days, or you have to, and that system in which you join together has to pay capital, and capital is greedy. You have to pay capital, and you have to pay management, and you have to pay them at rates that are very high. You have to pay technology, and you have to pay the villager. But my system that I've put together, and we're looking at it in Egypt right now, 30% goes to management and technology. 30% goes to the villager. 30% goes to capital, and capital is paid back on a first in, first out basis. So if I'm the capitalist, and this requires $1 million or $2 million or whatever, 10 crore, I get that 10 crore back before anybody gets a dividend. Okay. That's capital. Capital gets a first in, first out, and then he owns 30%. The villager has to be paid on the basis of, okay, I get X amount on an annual basis or a monthly basis for my labor and for my land. And that goes first before management, before whatever. So you have to capitalize it properly. You have to set it up properly. But in my opinion, that 30, 30, 30 and 10%, 10 guna, goes to, or 10% goes to government, goes to the panchayat, goes to the link person, go to other. Now, we are setting up a system right now in which we're trying to work with the government of Orissa, right, through the Patnaik's office. And they couldn't understand this, you know, 30, 30, 30. Well, the villagers are totally useless. You know, you can't give them 30%. So you have to. Once you give villagers 30%, they will basically do this aggregation of land. You know, a guy like, what's his name? Reliance, the head of Reliance. What's his name? Wealthiest man in India. I keep blocking it. Pardon? Ambani, Mukesh. Yeah. Mukesh says, you know, I have the best mango orchard in the world at my factory in Jamnagar. And yet I can't get land. You know, inko hata nahi sakta. That's Ambani. He can't get land in India because hatana, he was want to hatao, you know? So what you have to do is pay the villager, you know, not 1 lakh, not 2 lakhs, but try to get him for his 1 or 2 hectares, 1 crore per year. Once you do that with villagers, then land becomes no issue at all.
Yeah.
But
Paul,
you know,
Sorry to interrupt. Enrico has to leave because he has a meeting scheduled. I would like to thank Enrico, and then we can continue with the discussion. And also, out of all these systems, we haven't looked at one more aspect, that natural systems also help in ecological restoration, or they work towards the ecosystem and such. And I would like to ask Mr. Ajay Phatak, who's trustee of Ecological Society and ex-VP of Samsung, to conclude this session. We can still have the discussion, and to thank Enrico as well. So over to you, Ajay.
Sorry. Just one thing. I really need to go, but I would like to thank everyone. It was great, and I will watch the video and I will spam this video across. I have several friends and collaborators in circular economy, so I love the idea of producing bioplastics, and this is probably one of the best video one of the best meeting in the last year I have on that topic. So thanks, and well, see you next time on Zoom.
We have to talk biofilm sometime, Enrico. So
absolutely, I will send an email to your email in Silicon.
All right, very good.
Bye.
Thank you.
Bye.
Thank you, Enrico.
Thank you.
Yeah, over to you, Ajay. I think you have to unmute.
Yes, Prasanna, thank you very much. And it was a very interesting session, 3-4 different perspectives coming together. I would like to put forward a little bit holistic angle to all the different discussions that we have had. I think one of the key part that we need to understand is in nature there is no waste. And what does that really mean? And how can we learn from this whole principle that in nature there is no waste? So what are we really trying to do here? So if we really look at the human intervention over a period of long time, I mean human history right from the time agriculture began, we really see that today's world we have broadly 3 buckets in which we generate waste, or at least we call it waste. I mean, I don't believe that that's waste, but we call it waste. One is human waste directly, which is we call it sewage. Another is indirect waste, which we see from the industries. And the third is the indirect waste that we see from agriculture, very broadly. I mean, there are many more, but these are 3 very broad buckets from which we see, and whatever this output is, we call it waste. And one of the key aspect of why we call it waste is because of scale. At one point in time, when there were limited number of people doing limited amount of intervention, we did not really know that there was waste at all. And that was because natural systems were capable of ensuring that this waste was completely recycled. So it was basically nature's circular economy, if I will, at a point in time. Now, having said that, now we are at a stage where the volume and scale of these 3 buckets has increased enormously. Now we have to go back and ask this question: why have we increased this waste? Why have we increased this waste? And can we do something about it? Now, for example, if we take a simple case of a city like Pune, which has a lot of watershed, there are plenty of streams which enter Pune. And every stream is enormously polluted. And actually, if we go upstream, we really understand that every time there is a person trying to do something which he should not be doing with the stream, is causing the pollution predominantly and primarily, right? For that matter, historically, even when you are talking, and this is a point of debate, or for that matter, a counterintuitive aspect. But if you go historically, defecation, open defecation for that matter, has not had those kinds of problems, because we had counterbalancing vegetation, right? Counterbalancing vegetation was right there to make sure that it absorbed all the nutrients, and those did not overload streams, for example. Now that has completely changed over a period of time, and therefore you need all these scientific approaches to figure out what can you do once these issues actually land up in the nalas, for example, or what happens when you're adding a lot of nitrogen and phosphorus and agricultural runoff to your streams. So first thing for sure is we have to look at solutions which are upstream. And these upstream solutions may not be scientific, but they might be social. And it is important to look at these aspects as well. And as Paul from other perspective, rightly pointed out that, people will change behavior if they see return. And I'm pretty hopeful that, combining these approaches, where we are talking about people seeing returns and therefore they're willing to change behavior. End of the day, this behavior must change. Trying to see how important and how we can really, put all these things together in an upstream model to solve this problem a little bit more holistically. And this problem of waste is not just waste, in terms of water. You are creating all kinds of waste because of unseen amount of consumption, which also has to be, tackled in terms of trying to understand, what is really required and what is really not required, and how can we, tackle that as well. So, these are some of the aspects and perspectives which we need to look at when we want to do something using natural systems. So natural systems are great, but natural systems will have a limitation if we do not change our behavior at all. And if we want to see that this behavior changes, we have to, take some of the steps like what Paul was talking about, or Professor Dhanorkar was talking about, in terms of both return on investment, at the same time, a lot of research, which allows you to see how that can be enabled, right? So with this, I will, stop my basic comments, but at the same time, I would like to kind of paraphrase this discussion in a few lines. Part one is there are different methods available, and some of the interesting plants that we have observed over a period of time might make far more impact. Like for example, duckweed, azolla, or spirulina, what have you. Now, duckweed-based research has gone a long way, and I see that there is a great potential. And how we can, mobilize this potential or convert this potential into real solutions. We have been fortunate to have Paul, who has talked about real solutions, but we definitely need to see how these solutions can be implemented in India. For that matter, Prasanna and Pooja have, done a fantastic job to get started on this path, and I believe that there is an interesting way ahead to see how this could be packaged in terms of viable business models. And Paul has been supportive of suggesting how this can be done. At the same time, we are talking about need for research, and this research and how it can go into making some of these systems even more interesting in terms of lower cost of energy, in terms of easy maintenance, and these kinds of things. And third, but not the least important, is ability to sense and ability to make sure that there's some measurement. Now, whether it uses electrochemistry, whether it uses electronics, whether it uses conventional manual methods of collecting a sample and analyzing in the labs, is a different aspect. But this aspect of measurement, so that the management can really happen fully and properly, will also be a very crucial aspect. And we see that all these three things that we discussed today have one common purpose, and that common purpose is how can you say that you do not have waste at all. And all these waste, the so-called waste, is actually a resource, and it can be converted into something which is useful to not just human beings but whole of life. And also, it can make money in terms of economic contribution for that matter. So with this, I'd like to conclude this particular session. I'm pretty sure that there are more questions that might have been there or might be there even beyond this. I hope that all three members of this panel, Professor Dhanorkar, Paul, as well as Enrico, are available to us for consulting, for further conversations over a period of time. Thank you very much.
Paul, any remarks or?
You talk to me?
Yes.
Yes, I'm available for consultation. I like your comment that there is no waste. No, there is no waste. It's all an opportunity. So yeah, well spoken. I think you hit the nail on the head. Yeah, it is all an opportunity. I look at a place like Bangalore or Bengaluru, and they're running out of water. They're not treating their waste. Their tanks are burning because there's so much methane coming out of them. A huge opportunity. Bengaluru is an opportunity for all of us. So the question becomes how to get this out there and make it happen. I was invited to speak by Gadkari, and this in Delhi. And then he approached me behind the scenes. We can take care of your business and do it, etc. So there's so much behind the scenes stuff that happens. It's very difficult to make things happen up front. And that's an unfortunate problem, not just in India, but everywhere when it comes to infrastructure. So I think we all need to pull together. We all need to be partners with one another and begin to make this happen. So from my side, yeah, I'm trying things in Jodhpur. I'm trying things in Bihar and Jharkhand and wherever. But I've been quite clear to Pooja, whom I love, what a wonderful girl. If I get going, you're all on board, because we need to pull together to make these kinds of things happen. Now, I'm not going to be around for that much longer. And so I'm anxious to make it happen as soon as possible. Rural development in India, treating wastewater, drinking it. We should be drinking our wastewater. So thank you for putting this on. I mean, and yes, I'm always available. We need to speak about anaerobic digestion as an example. Right? You've done a lot of work in anaerobic digestion, and we do it in a way in which we use biofilm. We do it sequentially. Every system is sequenced. We deal with all of the volatiles up front. They're all broken down. So there is no waste that comes out of a biogas digester. Now, I've been watching in India and China, these systems that have been put out there since the 60s, and yet nothing works long term. They're designed in ways that are difficult to operate. Technology is given and not partnershiped. And so, we need to begin putting this kind of system out there. The only thing that should come out of a biogas digester is mineralized grit, stones, if you would, sand, nutrients, clarified nutrients, and methane. You can take the CO2 in those and use bacteria to actually methanate if you can find a little bit of hydrogen as well. I mean, you add a bit of hydrogen to the equation, so that's it. Mineralized grit, nutrients, clarified nutrients, and methane. Now, when you are producing that, and the amount of waste that's available to produce that is just beyond imagination. It's stunning. All of it makes money. Capture all of your CO2 that you use after you've burned your methane and run it back into your duckweed. We now know that when you add CO2 to your duckweed, build the levels up, the increase in production in duckweed is quite stunning with higher levels of CO2. We need greenhouses. So we need to make, so all of this, but duckweed is a magical thing. I mean, right now, NASA has decided on duckweed as what they're going to use in space. They're looking at doing it on Mars. How are they going to recycle duckweed? We've learned with duckweed that we can take light, and by pulsing light, we can, 20% of sunlight allows you to optimize production of duckweed. By pulsing light, they have discovered that they can use much less than 20% of sunlight and still get optimal response out of duckweed. Now, suddenly with LEDs and so on, you are talking about bringing the power right down. You can put a layer in 2 centimeters and you can build into a building, enhance the CO2 in that building, use pulsed light, and you can put duckweed systems anywhere and they will make money. Downtown Mumbai, where do you want to put it? It doesn't matter. We can put duckweed systems anywhere. And when we talk about natural systems, what is activated sludge? It's just growing a soup of bacteria that is uncontrollable. Nobody can really manage that soup of bacteria. So that bacteria is an organism. It's a bunch of organisms in an uncontrolled soup that uses lots of power. Duckweed, we can manage very specifically our duckweed. And it clones itself. We can engineer that duckweed to produce all kinds of magical things like enzymes, et cetera, et cetera, et cetera. When you put it in a building, we can still feed it with wastewater, and yet we can produce industrial enzymes. Though duckweed is magical. You guys are there sort of before it has really taken off. Let's do it. Let's do it. Let's make it happen.
Sure. Thanks a lot, Paul. And I think now we are running out of time, but thank you everyone for being here and all the participants. And if you want to contact us later, we can still keep this discussion on. And I think I would like this discussion or this session, which we try to organize for the Water Day. I would want this to be a starting point of a beautiful collaboration and some work that we'll do further using duckweed in collaboration with symbiosis, using electrochemistry and doing all the interdisciplinary work.
Exactly. That's what needs to happen.
And you have said, Dr. Paul, yes, even I had a very bad experience at Bangalore installing waste management systems. What you say upfront, what you work is different, and behind the scene, it's a totally different thing. It's very difficult for a private company to work in government organizations.
It's almost impossible. Yeah.
I know. I've experienced this for the last 10 years. So that is there. Of course, we are ready to welcome you with Prasanna, Pooja, and we are beyond this, your Rajasthan and Bihar. You're welcome to Maharashtra. We would love to collaborate with you and have some of these models installed in Maharashtra so that Gadkari will be proud of, as you say.
I am available. I can only do so much. I'm here to help anybody, and Pooja is a family member for me. So she's like my daughter.
Mr. Ajay Patak to support his statement and nothing is waste. Our center name is not waste management. It is waste resource management center.
Exactly.
So we look waste as a resource.
There is no waste.
Yes.
Absolutely.
Thank you so much.
Absolutely.
Thank you so much.
All right. Well, listen, I'm going to go to bed. It's late here.
So,
thank you.
Thank you, Paul.
Thank you, everyone, for joining.
Thank you, everyone.
And Paul, I hope to see you soon.
Yeah.
I hope so. Take care.
Yeah. Thank you. Thank you, everyone.